Hello, everybody. This is some practice problems that I'm going to go through to help you prepare for the first midterm in Physics 3300. So I've just written out four problems here that bear some resemblance to the types of problems that you'll get on the midterm on Thursday. And so I'm just going to go through each of these problems, solve them here, and talk through the solutions. And then you can use those for your preparation. So the first question is a question about the material derivative. Use the definition of the material derivative to show that for any function f of x, y, z, and t, that we have the formula that the material derivative of f squared, the square of the function, is equal to 2 times f times df dt, which is the same result that we would get for any typical function for an everyday derivative, like a partial derivative or a normal derivative. Okay, so how would we show this? We'll put the solution. So we just want to use the definition of the material derivative here. D by dt is defined as partial by partial t plus u dot grad, and u is uv w, and grad is d by dx, d by dy, d by dz. So u dot grad is u d by dx plus v d by dy plus w d by dz. So our whole operator here, d by dt, is equal to partial by partial t plus u partial by partial x plus v partial by partial y plus w partial by partial z. So what we want to do is just evaluate this operator on this square of this function here. So let's look at d by dt of f squared. So this would be partial by partial t of f squared plus u d by dx of f squared plus v d by dy of f squared plus w d by dz of f squared. And now for each of these regular derivatives, we can use the usual rules of differentiation. So this will give you 2 times f times df dt. This derivative here will give you 2 times f times df dx. This one would be 2f df dy, and this one would be 2f df dz. This is just by the chain rule. And so we have here, this is equal to 2f df dt plus, when I bring down our u, u times 2f df dx plus, bring down our v times 2f df dy plus, bring down our w times 2f df dz. And now there's a 2f in all of these terms. So we can write this as 2f outside of partial f partial t plus u partial f partial x plus v partial f partial y plus w partial f partial z. Now this whole thing here we can recognize as the material derivative of f, because we have the partial time derivative term, and then we have the 3 coordinate derivative terms. So this equals 2 times f times df dt, and scrolling up, that's exactly what we wanted. So we have shown that the material derivative of a square, once you go through sort of expanding out all of the individual derivatives that make up the material derivative, we get back out the same rule that we would get from applying the normal chain rule. So that's the solution to that one. And so the main takeaway from this is that you should be familiar with, for the midterm, the definition of the material derivative of this type, That will be given on the formula sheet, but you should be familiar with how to break that down into the 4 components, and how to just manipulate those components and use derivative rules and things like that. So you might get some kind of question about understanding the material derivative. Okay, next one, sketching a flow. So sketch and briefly describe the flow given by the velocity field in 2 dimensions, u of x and y equals x, and v of x and y equals y. So what's our solution? So we want to sketch this on the xy plane. And when we want to sketch a vector field, until you've done a lot of these and you're very familiar with it, the easiest way is just to pick some points in the plane and draw in the vectors at those points. So, and you can do sort of whatever you want, but it's usually sensible to pick points somewhere circulating around the center. And so I'm going to pick the 4 points here at 1, 0, 0, 1, negative 1, 0, and 0, negative 1. So let's evaluate u equals uv at the 4 points. And you could pick different points if you like. Xy equals 1, 0, 0, 1, negative 1, 0, 0, negative 1. So at 1, 0, we have u is equal to xy is equal to 1, 0, which is the rightward arrow. At 0, 1, we have u equals xy equals, so x is 0 in this case, and y is 1. So that is the upward arrow. At negative 1, 0, u is xy is equal to, so x is negative 1 in this case, y is 0. So this would be a leftward arrow. And 0, negative 1, u is xy is, so now x again is 0, and y is negative 1. So that's a downward facing arrow. So now we could draw these arrows on our diagram here. So they're going radially outward. And then if we look at the formula on x and y, it's kind of clear that if we, or you might imagine that in between these, the arrows are also going out this way. You wouldn't need to draw 8 points, just 4 is good enough. But the idea is that this flow is sort of radiating outward. It's diverging outward from the center. So our description would be this flow is diverging or spreading out from the center at x, y equals 0, 0. And that would be a sufficient answer for that one. So just understand how to be given a formula, a vector field that describes a flow, and then just represent that flow graphically. And you might also be asked, for example, to talk about how particles are going to move in such a flow or something like that. But in this case, you're just being asked to interpret the formula and then graph what the flow looks like and then describe it in words. And so that would be the full answer for that problem. Okay, so let's jump back into the third problem here. So this one is about the kinematic equation. So consider the flow in 1 dimension, so just a one-dimensional flow along x. So you can think of it as like flow in a pipe or something. Given by u of x equals ax squared, where a is a, let's say, positive constant. So a is greater than 0. Solve the kinematic equation for a parcel originating at x not positive at time t equals 0. Describe the motion of the parcel. Okay, so our kinematic equation, so here's our solution. So the kinematic equation is dxp dt equals u of xp of t and t. In our 1D case, we have dxp dt is equal to a times xp squared. So this is, and our initial condition is that xp of 0 is equal to x naught some positive value. So this is a separable differential equation. And on the midterm, if there's anything tricky, this one is pretty simple, but if there was anything tricky in terms of how to solve the differential equation, I would give a mathematical hint. In this case, it's very easy. We can separate like this, and then we could integrate both sides. So the integral so this is the same as the integral of xp to the minus 2 dxp equals the integral of a dt. And we can integrate here from x naught to xp and times 0 to time t. And so the integral of xp to the minus 2 is xp to the minus 1 divided by minus 1. And that's evaluated at x naught and xp, and that equals a times t minus 0. So we get here negative 1 over xp evaluated at xp x naught equals at. So we get negative 1 over xp minus 1 over x naught equals at. So we can do some rearranging. So I'm going to bring this over to this side and bring that over to this side. So we'll get here 1 over xp is equal to negative at minus 1 over x naught. So I realized I made a mistake here. In this, when evaluating this, it should have been 1 over xp, that part's correct, but this should actually be a plus sign because we have two negatives there. And so we actually end up with a plus sign here. Okay, that's good. So this is now correct. So now we can put these over the same denominator. So minus at x naught plus 1 over x naught. And then let's add a page here. So we can flip. So we have an equation so far. 1 over xp equals 1 minus at x naught over x naught. We can just flip both sides, and we end up with xp of t is equal to x naught divided by 1 minus at x naught. So this is our final trajectory. And what we can see is that as t increases, 1 minus at x naught decreases. So the denominator gets small, and xp of t grows. Parcel moves to the right. And something special happens here when 1 minus at x naught equals 0, the particle actually goes to infinity. And so the particle or parcel accelerates very rapidly, and we'll say reaches infinity at time t equals 1 over a x naught. And so, so the problem asked us to solve the kinematic equation and describe the motion. And so just to review here, we wrote down our kinematic equation. We got to this point. That's writing it down. Then we did our integral to get a separable, integrated our separable equation, a little bit of simplification. We get down to this formula. And then in terms of describing it, what we find is that xp is always positive, is moving to the right because this denominator is getting smaller, and then it actually goes to infinity in finite time. So basically, our flow is increasing like x squared. So as x gets bigger and bigger, the square of x gets faster and gets bigger and bigger also. So the parcel gets going faster and faster and faster, and actually runs all the way out to infinity in finite time. And this is like a little bit of a mathematical complication, so you might not get one with that particular trick or something that's actually going to infinity in finite time on the midterm, but this is a similar level of difficulty that you can expect. So separable equations, something like that, and let's do an integral and find the partial trajectory. Okay. So the last practice problem, so the test is going to be a mix of sketching, explanation, and analytical calculations. And so here are just some example explanation questions. You won't get these exact questions, but something similar. So explain. So part one is naively, one might expect that the acceleration a could simply be the partial time derivative of the flow. So this is the sort of proposed formula, which is not the formula we discussed in class. That's why I've written a question mark here over the equal sign. So explain in your own words why this is not the complete acceleration. It may help to think of an example flow in which partial u partial t equals 0, but parcels still accelerate. So for our solution here, we can think of, we did in class the example of a river. So we have a waterfall down here. And then we have a river that's accelerating. And if we look at the line right down through the center of a symmetrical river, from the top down, the velocity is not actually changing, but parcels, if you have a parcel that's flowing down the center, as the river contracts on two sides and gets narrower and narrower, the same amount of water has to go through a smaller space, and so the flow speeds up. So as our solution, we could say, consider a flow like u of x equals lambda x, which is the straining flow from class. The real acceleration is a is du dt is partial by partial t plus u d by dx of lambda x, which equals, so the partial by partial t part is 0, so this equals lambda x times d by dx of lambda x, which just equals lambda squared x. So parcels accelerate because the flow speeds up as x increases. Spatial gradient spatial gradient, so parcels. So there's a spatial gradient rather than a change in time. Accelerations can come from either gradients in space or explicit time dependence. Okay. And the last explanation question as part of the practice problems says here, without doing any calculations, state the net pressure force on a submerged cube, assuming that the pressure is uniform everywhere, we'll say in the fluid. So P of x, y, z, t is just equal to P naught, so that's just a constant. Briefly explain your reasoning. So we have a situation where we have, here's our water, the cube underneath, pressure equals P naught equals constant everywhere inside. And so we've got pressure forces acting on the walls of our cube, 6 pressure forces on the 6 sides. So solution, without doing any calculations, the force on each side of the cube is F pressure equals the pressure times the area. Because the pressure is uniform, all 6 pressure forces are the same strength. As a result, these forces perfectly balance one another. So the cube is squeezed, but the net force is 0. And so in this case, we don't need to do any explicit calculations, just based on symmetry considerations. We know that the net force is going to be 0. Okay, so just to review, so we talked about material derivative, understanding the material derivative, being able to do some manipulations with that. I gave an example here of you essentially showing that the material derivative obeys the chain rule. Sketching flows, so you're given a vector field, you want to be able to represent what that looks like graphically. Kinematic equation, so this could be 1 or 2 dimensions. We haven't really talked about it in 3 dimensions. So understanding how to write the kinematic equation for a particular velocity field, and then solve it and interpret the formula that you get. And then explanation questions. So anything that we sort of discussed in class, had a discussion about, and that would be, if you had time to rewatch the videos, anything where we sort of paused and I sort of elaborated on verbally, or that's elaborated on in the notes, would make for good explanation questions. And so the exam will be a mix of those types of questions. Okay, and please feel free to reach out if you have any questions about any of these practice problems, and best of luck in your preparation.